I think we all recognize that oil and water don't mix together, right? So here's a glass with water and oil, and you could stir that up until you got sore muscles, and as soon as you stop, it'll begin to separate. The oil will come to the top because its density is less, and the water will be at the bottom because it has a higher density. But why do they separate? There's something about the water molecules that causes them to bunch together. They're very attracted to each other. They're basically very cliquish, and they won't let the oil in. You can stir it up, but as soon as you stop that, they push the oil out. When we look at the Lewis structure for water, we see that the oxygen has two lone pairs, and each of the hydrogens is bonded to the oxygen with a single bond. And so we see this pair of electrons that's shared between the hydrogen and oxygen. But when you share with someone, the sharing is not always perfectly equal, is it? You ask the one child to share the cookie with his brother, and he breaks it in half, and yeah, he shared, but one half was a lot smaller than the other half, right? And that can cause World War III in the playroom. So what's happening here is in this sharing of this pair of electrons, oxygen hogs the electrons. Okay, it takes them away from hydrogen. Is it still sharing? Yeah, and hydrogen's going to stick around because of it, but they're not shared equally. So here we have electronegativity. So electronegativity can be defined as the ability of an element to attract electrons within a covalent bond. Oxygen is more electronegative. It's more attractive to the electrons in that bond. And so those electrons, those shared electrons, are more likely to be found closer to the oxygen atom than to the hydrogen atom. You would think, well, they're sharing, it should be evenly spread around, but no, it isn't, it's lopsided. Electronegativity is just a relative man-made scale, and what they did is they took fluorine, which is the most electronegative element, and they just said, okay, we're going to call fluorine 4.0, and we'll measure everything else relative to that. So fluorine's the most electronegative. When we look at a bond between an oxygen and a hydrogen, oxygen is more attractive to that shared pair of electrons than hydrogen is. So this would be like those orbital diagrams, not the orbital diagrams, but the orbital pictures of the s and the p orbitals, right? So imagine taking a picture over and over and over again to see where that pair of electrons is. And what you're going to find is that there's more, they spend more time over here around the oxygen than they do around the hydrogen. Oxygen has 8 protons, and hydrogen has 1 proton. And so if there's extra electron density over here, that's going to cause this end of that bond to be a little bit negative, because those negative electrons spending more time over here, this is going to be slightly negative. This is going to be slightly positive because the electrons aren't spending as much time over there. We can symbolize that with this lowercase Greek delta. It looks like a lowercase d with a posture problem. D minus means a partial negative charge. These aren't ions. It's not that the electrons were transferred, but they're just not shared equally. So I have an analogy for this in chemistry land. Electrons are a lot like little boys. So Andrew's 8, and he's squirrely like an electron. He's getting better, but he's still pretty squirrely. So here's oxygen house, and here's hydrogen house, and each of them has a little boy, and they're going to share, they're going to play together, okay? So oxygen sends her little boy out, and hydrogen sends her little boy out, and they play together as a shared pair of electrons. Over at oxygen's house, they have a big screen TV, they've got all the cable channels, they've got a soda fountain in the kitchen, and Mom will order pizza for you if you're hungry. Over here, hydrogen has a black and white TV with a VCR with Thomas the Tank Engine videotapes. And if you're hungry, she'll give you bread, they don't even have any butter, and some water straight out of the tap, not even ice, right? So where are those two little boys going to play more? They're going to play at oxygen's house. they're not sharing equally in their time between the two houses. Why? Because they're more attracted to oxygen. It's more fun to be over there, right? So this end is slightly negative, and this end is slightly positive. Another way that we can symbolize that is with a line, an arrow. So an arrow that points to the more electronegative element, and we put a little plus on the positive side. And so this is indicating that this bond is not sharing equally with electrons, that this is more electronegative. And I think of this as the neighbor, the guy across the street. He's out working in the yard, and Dad comes home and wants to know, hey, where are those two little guys? And the neighbor points, they're over there, right? He's going to point to Oxygen's house, because that's where they're going to be. They're going to be over here. It's not an ionic bond. In an ionic bond, oxygen would actually adopt hydrogen's kid, right? Hydrogen still goes home to sleep. That's where his clean underwear is. His mom, he goes to see his mom once in a while, but most of the time he spends over here. Does that make any sense? Okay. So that bond is lopsided. One end is different than the other. That's called a dipole moment, when one end is different than the other. We think of the Earth, and we have the North Pole and the South Pole, and it has to do with magnetic fields. But one end of our globe, end is, how do you say end on a sphere? But there's one point that's more negative and one's more positive in terms of poles magnetically. So bonds can be like that too, one end being different than the other. So this is a polar covalent bond. It's covalent, the electrons are being shared, but it's polar because one end is different than the other. So the bigger the electronegativity difference, the greater the dipole moment, and the more polar the bond is. If those two houses have very similar stuff that's attractive to 8-year-old boys, then they're going to be more equally distributed in terms of how much time they spend at each house. The bigger the difference between the fun stuff, the bigger the difference in the amount of time they spend there. This is a graphical representation of the electronegativities of the different main group elements. And so here we see fluorine is the top. Fluorine's 4.0. And as we move away from fluorine in any direction, it goes down. So this is also a periodic trend in the periodic table. If you can remember that fluorine is the ultimate kid house. They've got a swimming pool with a slide and a diving board, and they've got a trampoline. I mean, they've got a bounce house that's always on. This is the coolest. Yes?
That's very similar to ionization.
The trend, all of the trends tend to, like this one is increasing across and decreasing down. And all of them are either that or the opposite of that, right? And so this is actually going to be the same as ionization energy. As you go across, ionization energy increases. As you go down, it decreases. Yeah. But why are the noble gases not on here? They don't react much. They form very, very few covalent bonds. And so they're just completely left out. We just don't even think about it. Yes?
Will we represent the magnitude of that dipole moment, or is that just conceptual?
It's more conceptual in Chem 3A. We need to know that there is a dipole moment.
It's not like there's plus or...
No, we'll get to that distinction in just a minute. Notice that there are some exceptions, and some things like nitrogen and chlorine are both the same electronegativity, and you wouldn't necessarily predict that just by looking at the periodic table. I'm not going to have you do anything with the actual values of the electronegativity on an exam, just understanding a trend. And of course, hydrogen has to buck everything and mess it all up. So if we have two elements in a covalent bond with the same electronegativity, say 2 chlorine atoms, well, those electrons are going to be shared completely equally. Okay, this is like, this this house and that house, they have exactly the same stuff. I mean, they're just like identical houses. So why would the kids spend more time at one or the other? There's no reason. They're the same. So this is going to be a nonpolar covalent bond. There's no difference in one end or the other. So what I want you to know is that any bond between two atoms of the same element is nonpolar. If the atoms are the same, it's nonpolar. If we have a really big electronegativity difference, we're going to have a complete transfer of the electron from one atom to the other, and they'll form ions, and we get an ionic bond. Okay? So ionic bonds are common between metals and nonmetals. So if you see a metal and a nonmetal, that's an ionic compound. We've already learned that when we learned to name things. Metals and nonmetals, their electronegativity difference is so great that the electron is actually transferred. But if it's metal, nonmetal, it's ionic. What about in between? That's the polar covalent bond. Here's hydrogen and fluorine. Fluorine is more electronegative. It's the most electronegative. So this end is partially negative, and the hydrogen end is partially positive. Polar covalent bonds are common between two nonmetals. If they are two different nonmetals, I would expect you to say that it's a polar bond. Are there exceptions? Sure there are. Carbon-hydrogen is the only one you should even try to be aware of. If the two elements are the same, nonpolar. Metal, nonmetal, ionic. Two different nonmetals, say it's polar. So it's actually a continuum from zero difference in electronegativity between the two atoms up to the maximum is 3.3. And so, as with many things, you have to just put dividing lines in there somewhere. Because how do you decide if someone's rich or poor? Well, somebody arbitrarily says, well, if you've got this much money, you're poor. And if you've got over this, you're rich. Well, they just picked a number, right? So here we've picked numbers. There's, some reasoning behind this. But 0.4 and 2.0 are the breaking points. Now, do you need to remember those? No, you can look them up in any homework problems, and I won't give you anything like that on an exam. But you look at the electronegativity difference. So, examples here, pure covalent, I prefer the term nonpolar. Nonpolar covalent. Chlorine and chlorine, two atoms the same. Yes?
What if something's like on the border of difference?
That's a good question. What if it's on the border? So if it's on the border, like between nonpolar and polar, if it's 0.4, those are going to be two different elements, and I'd expect you to say it's polar. A large difference is going to be an ionic compound. And of course, there's subtleties to this that we're just not going to get into here. But if you've got two of the same element, rather than spending a lot of time trying to figure out what's really just an arbitrary difference, what I want you to have is an understanding that'll work most of the time, and it doesn't take too much time to memorize. So two elements, two of the same element, they have to have the same electronegativity, so that's going to be nonpolar. This would be two different nonmetals. And this would be metal and nonmetal. So by looking at the two elements in a bond, you should be able to tell me, is it a nonpolar covalent bond? Is it a polar covalent bond, or is it an ionic bond? And the only exception to this one, and I won't test you on it, a carbon-hydrogen bond is nonpolar. If you remember that, it'll make some of the other stuff make a little more sense. If you don't remember it, you'll be fine anyway. Okay, so we're going to look at bonds between different elements here and ask, are they pure covalent scratch that out and write nonpolar. Are they nonpolar, covalent, polar, covalent, or ionic? So if we have iodine and iodine, what kind of a bond would they form? Nonpolar. How about cesium and bromine? Ionic. So you have to find the elements on the periodic table, and we see that cesium's a metal, bromine's a nonmetal. So that, therefore, it's ionic. You don't actually have to look at their electronegativities. Phosphorus and oxygen. Polar. Polar covalent. Because they're different. Okay, on an exam, I'm not going to give you the table of electronegativities and ask you to subtract and identify, well, is it more than 0.4, less than 0.4? Just assume. And I won't try to trick you. Okay, so we're going to combine polar bonds with molecular shapes. You can have a molecule that has polar bonds, and yet overall the entire molecule is not polar. A polar molecule is one that has a net dipole moment. Those polar bonds add together instead of canceling each other out. So dipole moments are a bit like vectors. Do you remember at least hearing about vectors? Vectors are arrows. They have a length, a magnitude, and then they have a direction. And so you can add them together in three-dimensional space. And that might bring up nightmares or something from math class. If you've got a diatomic molecule, those are pretty simple. There's only one bond. If the bond is polar, the molecule's polar. When you have more than two atoms, things get a little more complicated. Let's look at carbon dioxide. So we learned how to predict that carbon dioxide is a linear molecule. By looking at its Lewis structure, there are two electron groups. They're going to be on opposite sides. This carbon-oxygen bond is polar. These are two different nonmetals. This is a polar covalent bond. Oxygen is more electronegative. It's closer to fluorine on the periodic table. And so oxygen is pulling these shared electrons away from carbon. And over here, this oxygen is pulling the shared electrons away from carbon. You can think of this as playing tug-of-war. So here we've got a rope, and there's the middle of the rope, and somebody's pulling on this side, and someone's pulling on that side. The people are equally strong. Is anything going to happen? Is the rope going to move? No, because the people are pulling in opposite directions. Those are vectors canceling each other. This is a nonpolar molecule. One end is not different from the other. There's not a positive and a negative end because they cancel each other out. So it has polar bonds, but they cancel each other out. So we can represent the polar bonds as arrows or vectors that point in the direction of the negative pole, have a plus sign at the positive. If those arrows point in exactly opposing directions, the dipole moments cancel, and we have a nonpolar molecule. Let's look at water. So this is a molecular space-filling model of water. Here is a structural formula. We're not showing the lone pairs there, but because of the lone pairs, water is a bent molecule. So this oxygen-hydrogen bond is nonpolar. I'm sorry, it's polar. Oxygen is more electronegative. It's hogging the electrons. Hydrogen, oxygen over here. Again, a polar bond. Oxygen is hogging the electrons. So if we think about tug-of-war again, here's the middle of the rope, and somebody pulling this way and somebody pulling that way. Is the rope going to move? Yeah. The rope's going to move in this direction. That's what happens when you add vectors. This is going to have a dipole moment. It's going to be a polar molecule. The oxygen end is going to be more negative than the hydrogen end of the molecule. Any questions? So here the book is showing you, how to determine if it's polar and adding the vectors and stuff. My experience is that Chem 3A students don't like to think about things like this, and that's fine. I'm getting to something that'll be simpler. So this is the method. You figure out if the molecule has polar bonds. If it doesn't have polar bonds, you don't have to go any further. Then figure out if the bonds add together to form a net dipole moment. Use Vesper theory, and is the molecule symmetrical? Or there's Mrs. K's alternate method. Look at the Lewis structure. It will be nonpolar if both of these things are true. There's no lone pairs on the central atom, and the atoms bonded to the central atom are all the same, or have the same electronegativities. So this is much easier to remember, and it works really well. Does it work every single time? No, but it's plenty good enough for Chem 3A. So let's do some examples. Determine whether CH4 is polar. Well, we need the Lewis structure. So here's the Lewis structure. Are there any lone pairs on the central atom? No. So no lone pairs. Are all the atoms bonded to the central atom the same? Yep. This is a nonpolar molecule.
What was the second rule?
The second rule is all the atoms have to be around the central atom have to be the same or have the same electronegativity. So this is nonpolar. Because when we make the model, we can see that those bonds are opposing each other. They're spread out in three-dimensional space. And if all those atoms have the same electronegativity, then the strength of those dipole moments are the same, and they're going to add up to 0. If we have a lone pair, though, that messes everything up, because the lone pair doesn't have a dipole moment. It's just nothing in terms of that. And so now all of these are pulling in the same direction, and this is going to have a dipole moment. It's going to be a polar molecule. So if you see a lone pair on the central atom, that makes it lopsided. It's going to be polar. Let's just look at another example. What if I put something different? If I took one of the hydrogens off and put a chlorine in. Now, of course, the chlorine would have some lone pairs on it. What about this molecule? Polar or nonpolar? Polar. It has no lone pairs, so it's nice and symmetrical, but this chlorine is different. This one's different than these hydrogens. And so this is going to pull electrons differently than the hydrogens will. So this is polar. Both of those have to be true for it to be nonpolar. No lone pairs on the central atom, all the atoms the same. Any questions? Determine whether ammonia is polar. You got to start with the Lewis structure. There's the Lewis structure. Polar or nonpolar? Polar.
But it has the lone.
It has a lone pair. If it has a lone pair, it's polar. Keep doing that. The lone pair disrupts the symmetry. So to be nonpolar, no lone pairs and all the atoms are the same. Has to be both. Here, all the atoms bonded are the same. They're all hydrogen, but there's a lone pair and that messes it up. So it's going to be polar. What about SO2? Now you cannot just look at the formula, because how do you know if there's lone pairs or not? You gotta draw the Lewis structure. We'll put sulfur in the middle and an oxygen on each side. 3 times 6, 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. We got to share. So there's our Lewis structure, one of them. There's a resonance structure. Is there a lone pair in the central atom?
Yes.
Yep. So is it polar or nonpolar? Polar. If you just look at the formula, you say, oh, well, that's symmetrical. One oxygen on each side, that's nonpolar. No, that lone pair messes it up. CO2 is nonpolar, SO2 is polar. This is the explanation for why oil and water don't mix. Water molecules are polar. Oil molecules are nonpolar. So the water molecules are attracted to each other a lot like magnets are. So this hydrogen end is slightly negative, the oxygen end is slightly positive, and so there's an attraction between them that is not present between oil molecules. So the water molecules essentially clump together and push the oil molecules out. It's a little bit like these are magnetic marbles. The solid colored ones are magnetic, and the others are the glass marbles. And you can imagine what would happen. I need to get some of these marbles because I want to play with them. The magnetic ones are going to stick to each other, and they're going to push the glass marbles out. That's what happens when you try to mix oil and water. The water molecules are literally stuck on each other. They stick together and they exclude the oil. You probably know from experience in life that oil and grease, things like butter, they do not just wash off your hands with water, do they? It just stays. Like, what the heck? Well, oil and water don't mix. Grease and water don't mix very well. And so the grease would rather just stay on your hand. So we use soap. And soap has a structure similar to this. This is carbons and hydrogens. This is a nonpolar section. Remember, I said that carbon-hydrogen bonds are nonpolar. And this is very symmetrical, and there's no lone pairs over there. So this is nonpolar, and then one end of this long molecule is polar. So this polar head is attracted to the water molecules, and the nonpolar tail is attracted to the grease. And so what happens is you get these, so here's the polar head, and then, oh, I started doing that backwards, that's okay. So the nonpolar tails of the soap molecules will stick into the grease, and then the polar heads will be on the outside, and those get along really well with the water. So the soap takes the grease and breaks it up into little micelles. They're surrounded with soap, and then the water sees the polar head of the soap, and we're like, oh yeah, you're one of us, you can come through just fine. And it's able to go away with the water. So that's how soap works. Any questions?